Hi, my name is Manish Gupta, and in this video, I'm going to talk about a recent embedding method called as NV-Embed. It's basically about some interesting improved techniques for training large language models as embedding models, generalist embedding models. So let's get started. Let's try to understand what is NV-Embed and how is it trained, right? And before we get there, in fact, let's try to understand and list down popular embedding models as of today. Right? So the initial embedding models were bidirectional models, bidirectional transformer-based models. For example, sentence BERT and SimCSE were BERT-based models which were fine-tuned on natural language inference datasets. More recently, people have proposed these models: MBI, Embed Large V1, UAE Large V1, Voyage Large to Instruct. Right? These are popular bidirectional embedding models. The recipe to train these models is in three steps. The first step is to initialize from pre-trained BERT or T5 encoder. Right? Second step is basically to pre-train it further with contrastive learning on curated, unsupervised or weakly supervised text pairs. So that's that. And the third step is essentially to fine-tune on variety of supervised data, most commonly using MS Marco, so that it learns how to do retrieval kind of tasks. Right? So as I mentioned, traditionally embedding models have been bidirectional in nature. But more recently, people have observed that decoder-only large language models can also serve as good embedding models. And in fact, people have shown that decoder-only LLM-based embedding models actually perform better than bidirectional embedding models, right? So the recent ones essentially include text embedding 3 large from OpenAI, E5 Mistral, SFR embedding Mistral, Google Gecko, and RetelM from Microsoft. Right? There is also, this model NV-Embed, which is what this video is all about. And NV-Embed, as you can now understand, is a decoder-only large language model-based embedding model, LLM-based embedding model. Okay. So the way this NV-Embed model has been trained is that we start from Mistral 7 billion. So basically, the architecture of NV-Embed is exactly the same as the pre-trained Mistral 7 billion, and then it is fine-tuned using LoRa. So low rank adaptation, right? So a way to fine-tune models very, very efficiently. Okay. So the architecture of NV-Embed is shown here. It basically takes input tokens, right? And then it uses a decoder-only large language model. So a pre-trained Mistral 7 billion. Now what it does is to essentially replace the causal attention in this architecture by bidirectional attention. So basically, although it initializes using the weights from Mistral 7 billion, but it removes the causal attention mask and therefore makes it bidirectional attention. So after you essentially have outputs from a decoder-only LLM, typically people get the representation, the embedding, in two possible ways. One is to basically look at the outputs of the tokens associated with the input and do a mean pooling over them. The other is to basically, if the input had 4 tokens, then you would basically take the representation of the last token as a representation, or the end of the sequence token as a representation of the input. Okay, but NV-Embed does a special kind of pooling using something called the latent attention block. Now, this latent attention block essentially looks like this. So it essentially follows the Perceiver IO architecture in some ways, but let me actually try to explain what it does. So it basically takes the output from the last layer of the decoder-only LLM, and that's basically shown here, and it uses them as queries in the attention block, right? The keys and the values are initialized with the randomly initialized vectors, and of course they are trained over iterations. And when the LoRa fine tuning is done on for NV-Embed training. Okay, so these latent arrays, in fact, they basically use 512 vectors, 512 such vectors. They serve as both keys and values. And then the typical QKV happens. So this is the Q matrix. This is the Q matrix, right? And this is basically the K matrix. And this is QK transpose going on in orange color. Softmax is applied, and then this is the value matrix, and therefore QK transpose softmax multiplied by V is basically what is happening there. After that, an MLP is applied, a multi-layer perceptron, so as to get the output, which is basically mean pulled. Okay. So this mean pulled output is basically the output embedding as predicted by NV-Embed, as obtained by NV-Embed. Okay, so that's basically the broad architecture of NV-Embed. It's more or less same as the Mistral 7 billion, except for two changes. The causal attention mask is removed so as to have bidirectional attention, and there's an extra latent attention block which is added for pooling and getting the final embedding. Now the training for NV-Embed is done in two steps, two-stage, contrastive instruction training, right? In the first stage, basically, they just tune on retrieval tasks, retrieval datasets, several of them, and I'll talk about more in detail on the next slide, right? Using in-batch negative sampling. And also curated hard negative example. So basically for these retrieval datasets, they actually obtained curated hard negative samples and also in-batch negative sampling. And then they do contrastive training. So that is the first stage. The second stage basically extends this training to non-retrieval tasks also. So including classification, clustering, and semantic similarity tasks. Okay. So they do not do any in-batch negative sampling. Okay. So basically two stages. The first stage is essentially the retrieval stage, contrastive training, but with the in-batch negatives and curated hard negative examples. And the second one is basically a mixture of four different kinds of tasks: retrieval, classification, clustering, and semantic similarity, but without any in-batch negatives. Okay. What training data is used for NV-Embed? Well, NV-Embed uses a whole bunch of data sets, as you see. All of them are organized in a contrastive training kind of a way. By the way, both the stages basically use contrastive training. So both of them actually make use of contrastive training, right? So therefore, all the data sets that you see here, whether they are retrieval data sets, or they are semantic similarity data sets, or they are classification data sets, or they are clustering data sets, all of them are organized in a contrastive format, which basically means that you have the instruction, this is the instruction template, along with the query. That's the input, right? And then you basically, given a document, a positive document, you try to give it a higher score compared to multiple hard negative documents. That's a typical contrastive formulation, right? So the relevant QD pair should basically have higher similarity compared to the irrelevant QD pair, QD minus pair in that sense. Okay, so that's that. So as you see, these data sets basically span four different tasks. The first one is retrieval. The second one, as I mentioned, is semantic similarity. Third one is classification, and fourth one is clustering. And again, lots of samples. So overall, they possibly add up to a few million samples. And the important thing to note is that they do not make use of any synthetic data set from GPT-4, unlike most other embedding-based models, recent embedding-based models, but they just make use of publicly available data, which means that it is completely reproducible, by anyone who wants to reproduce their results. Right. They perform evaluation on the popular MTEB benchmark. MTEB benchmark is basically a 56 task benchmark. These are the various tasks in the MTEB benchmark. As you can basically see, there are several tasks here. So there are these retrieval tasks that you can see right at the top. In fact, these 15 retrieval tasks that you see together are actually also called as the BEIR benchmark. So BEIR is like a subset of the MTEB benchmark. And then there are classification tasks. There is also semantic similarity task. There is clustering tasks. And there are many other tasks, right? So there are multiple tasks, and you can pause the video to basically see what each of those tasks does. So for example, maybe you can just look at this. Twitter URL corpus, this task basically retrieves the tweets that are semantically similar to the given tweet. So there's a tweet, there's a large tweet collection, and you want to retrieve semantically similar tweets. Okay? So there are many interesting tasks in this MTEB benchmark, 56 different tasks. So it's a large benchmark in that sense, and they perform evaluation on this MTEB benchmark. So how does NV-Embed perform on the MTEB benchmark? Well, an MTEB, by the way, is the most popular benchmark for evaluating embeddings these days, right? So on this benchmark, which basically comprises, as I mentioned, 15 retrieval, 4 reranking, 11 clustering, 3 pairwise classification, 12 classification, 10 semantic similarity, and 1 summarization task, right? Totally 56 different tasks. NV-Embed, when compared with many other popular, the state-of-the-art, embedding models, actually is at the top of this leaderboard, right? So NV-Embed is at the top of the leaderboard. Now so this is the leaderboard. In fact, this is basically in the order of decreasing average score across the 56 different benchmarks, 50 different tasks, right? And as you can see, Voyage is here, SFR embedding is there, GritLM is right there, Google Gecko, E5 install, all of them are there, right? NV-Embed is right at the top of the leaderboard. Okay. So it basically established a new state of the art of 69.32 on the MTEB benchmark. And if you just look at the BEIR benchmark, which basically comprises of these 15 tasks, NV-Embed leads to 59.36, which is again state of the art, which is again the largest compared to anyone else on the leaderboard. So in summary, in this video, I talked about the NV-Embed model. From an architecture perspective, it follows the same 7 billion Mistral architecture. However, it has an extra latent attention layer at the end, and basically it removes the causal attention mask. The training comprises of two different contrastive instruction tuning stages. The first one, which basically tries to train the model on retrieval tasks with in-batch negative sampling and manually created hard negative samples. But the second stage basically brings in these classification, clustering, semantic, textual similarity tasks without any in-batch negative sampling, but with contrastive training. Right. This NV-Embed model is super important because it is state of the art on MTEB benchmark and also on the BEIR benchmark. Okay, so that's it for this video. Thank you for watching. I hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.